Welcome back. This video is all about exponential and logarithmic equations. And up until now, we've solved various types of equations and situations that involve polynomials and rational functions. And now we see what happens when we have an exponential or a logarithm and try to find the value of x that works for our particular equation. So we've got a few examples here leading you through. The first four are kind of like the level 1 examples, and then we got a couple of the tougher sort of examples that'll get you through here. So our introduction, if you remember when we first started talking about exponentials and logarithms, all right, we knew that the exponential and the logarithmic function are inverse functions of each other. So some properties that'll be important to relate these is that if we knew that a to the x is equal to a to the y, then we knew that x is equal to y. And then the same thing, if log base a of x equals log base a of y, that means x also has to be equal to y in that situation too. So the whole idea is that if we can get down to the same base or to the same logarithm, then we'll be able to set the inputs equal to each other. As a reminder, exponentials and logarithms are inverses of each other. So something like a to the log base a of x is equal to x, right? So you end up back where you started. And log base a of a to the x is also equal to x. So this can be combined into one major trick when we're trying to solve an exponential equation. If you can isolate the exponential or the logarithm, then use the inverse properties of the function to actually solve for x. For example, if you see that 5 to the x is equal to 27, notice the x is part of the input here. But if we use our inverse properties, we would know that log base 5 of 27 equals x. You switch your input and your output. And so we can solve for x right away, since log base 5 of x is the inverse of 5 to the x. So, for example, solve 7e to the 2x is equal to 20. So in this case, the whole idea is that we want to isolate the exponential before using that inverse property. So I divide both sides by 7. If I do that, I get e to the 2x is equal to 20 over 7. Now I'm going to use my inverse property by taking the natural log of both sides. Well, why the natural log? Because the natural log of e to the something is the input inside. All right, so if I take the natural log of both sides, I get natural log of e to the 2x equals natural log of 20 over 7. And so we're left with just the input when we do the natural log of e to the input. So 2x is equal to natural log of 20 over 7. And dividing by 2, we get x equals natural log of 20 over 7 divided by 2. And our calculator tells us that that's 0.525. Let's say we want to solve 3 to the x plus 2 equal to 7. All right, so same sort of idea here. If we use our inverse properties, we know that we can rewrite this as a logarithm because we've already isolated our exponential function here. So if we switch our inputs, x plus 2, and our output of 7, we would get log base 3 of 7 is equal to x plus 2. So those are our inverse properties. One of our properties, of course, that we know from before is the change of base property. So log base 3 of 7 is the same as log of 7 divided by log of 3. So I can rewrite this as x plus 2 equals log of 7 over log of 3. And then when I subtract 2 from both sides, I get my final answer of log of 7 over log of 3 minus 2, which is about negative 0.229. So again, there's one major trick when we're trying to solve a logarithmic equation, just like with exponentials. If we can rearrange the equation so that we can use our inverse properties, that is isolating that logarithm by itself, then we're going to be able to transfer it into being an exponential situation. For example, if we see log base 6 of x is equal to 3, we can rewrite this as 6 cubed is equal to x, switching our base, switching our inputs and our outputs so that 6 raised to the 3, this base raised to the output power, is equal to x, since 6 to the x is the inverse of log base 6 of x. So as a way of an example, solve the following logarithmic equations. Solve log base 2 of x plus 2 is equal to 5. So we've already isolated the logarithm. That means we can rewrite this as 2 to the 5th is equal to x plus 2. So I switch my input and my output with 2 as my base. We also know that 2 to the 5th is equal to 32. And if I subtract from both sides, I find out that x is equal to 30. If you plug 30 back in, by the way, hopefully you can see right away, based on our logarithm discussion, that we get log base 2 of 32. And since 2 to the 5th is 32, it works out nicely. the second example, we have natural log of x is equal to 8. So as a friendly reminder, natural log of x is log base e of x. And so that means we can write natural log of x equal to 8 as x equals e raised to the 8, since this is base e, excuse me. So x is equal to e to the 8. Simple as that. All right, example 4, adding another layer to this. So we haven't isolated the logarithm. We've got 4 plus 3 log of 2x is equal to 16. But we can handle this because we need to isolate that logarithm first. So we can subtract 4 from both sides to get 3 log of 2x equals to 12. Dividing by 3 gets the logarithm all by itself, so that log of 2x is equal to 4. And now if you remember, log stands for common log, that's base 10. If I raise everything, do exponentiate, and I say 10 to the log of 2x equals 10 to the 4th, I'm in good shape because the 10 and the common log will cancel out as inverses do, and we're left with just the input. So 2x is equal to 10 to the 4th, and x is equal to 5,000. All right, here's one that's a little more challenging. We've got 3 raised to the 5x minus 1 equals 2 raised to the x plus 3. Notice our bases are different in this case. So what in the world do we do? Well, the first thing that's usually useful is to take the natural logarithm of both sides. And the reason why that's helpful is because we have a logarithmic property that allows us to move our exponent down as a coefficient. So if I take the natural log of both sides, I get natural log of 3 raised to the 5x minus 1 equals natural log of 2 raised to the x plus 3. And that property with our exponents and our coefficients allows us to move the 5x minus 1 out front of the natural log of 3. So I end up with 5x minus 1 times natural log of 3 equals x plus 3 times natural log of 2. Now the question is, how in the world do you get your x's? All right, well, we want to try to distribute first and then gather all our terms with an x on one side, because eventually we're going to factor out an x and solve. So here, when I distribute, I get 5x natural log of 3 minus natural log of 3 is equal to x natural log of 2 plus 3 natural log of 2. I've got two terms that have an x in it, so I'm going to subtract x natural log of 2, all right, to the left side, and I'm going to add natural log of 3 to both sides to make it go over to the right side. So I've got 5x natural log of 3 minus x natural log of 2 equals natural log of 3 plus 3 natural log of 2. And then finally, I've got all my x's on one side, so I can factor out an x to get x times 5 natural log of 3 minus natural log of 2 equals natural log of 3 plus 3 natural log of 2. And if I divide by 5 natural log of 3 minus natural log of 2, I get my x value. The calculator will tell you that that's 0.662. All right, our final example, log of x plus 2 plus log of x minus 1 is equal to 1. All right, so another hint for solving these logarithmic equations is to try to use our log properties whenever you can. And if you remember, if you add two logs, what you can do is multiply their inputs. So log of x plus 2 plus log of x minus 1 becomes log of x plus 2 times x minus 1, all equal to 1. So now I've got all this into one log. Remember, that's the whole point. We want to condense or figure out how to get everything into one logarithm. And since this is common log, again, I can write this as 10 raised to the log of x plus 2 times x minus 1 is equal to 10 to the first. So I exponentiate with 10 as my base. When I do that, 10 raised to the log of something is the something that's inside. So I get x plus 2 times x minus 1 is equal to 10. And now we just have an equation that's a quadratic that we need to solve for x. So when I distribute, I get x squared plus x minus 2 equals to 10. In other words, x squared plus x minus 12 is equal to 0. And I can factor this into x plus 4 times x minus 3, which I said equal to 0. And I eventually get negative 4 and 3. Now, on a problem like this, you got to be careful, because when we combined our logarithms, we created a product on the inside that didn't exist beforehand. And there's an issue with that, because if you multiply two numbers, there are two ways you can get a positive number. Remember that our inputs for our logarithms have to be positive. So the two ways that you get a positive number is if you have a positive times a positive, that's a good thing, because then both of your numbers originally plugged in would be positives. Or you could have a negative times a negative. But if I have a negative inside my logarithm as my input, that's a problem. That's not part of our domain. So we always need to check for what we call extraneous solutions. We're going to test our solutions by plugging them back into our original. And if we try out -4, that's not in the domain of either of these original logarithms. What happened was we had created a situation where we had a negative times a negative, which made a positive, which worked down here when we were working out this problem, but it didn't work for the original. All right, so it's not in the domain of the original logarithm, and x equals to 3 is, so x equals to 3 is the only solution that works. -4 is extraneous. We've been through a lot here, but the principles of solving exponentials and logarithmic equations are very similar to solving any other equation. And we got our properties of exponentials and logarithms to help us out, so know them well. Thanks for listening. We'll see you in the next video.